Atoms form the very foundation of the universe, acting as the building blocks of all matter. Their basic structure reveals an intricate design where the nucleus, a central hub imbued with a positive charge, anchors the atom. Surrounding this nucleus are electrons, negatively charged particles that orbit in well-defined paths. These components, though incredibly tiny, hold the secrets to understanding the universe's most fundamental principles. The journey to uncovering the atom's structure began with early models that sought to conceptualize its form and function. One prominent representation was the solar system model, likening the dense nucleus to the sun, with electrons resembling orbiting planets. However, this analogy was fraught with challenges. It failed to explain why charged particles, such as electrons, did not emit continuous radiation while orbiting, a process that would ostensibly lead them to lose energy and spiral into the nucleus. Moreover, scientists observed that atoms emitted radiation at specific frequencies, contradicting the expectations of the solar system model. These inconsistencies led to further explorations and breakthroughs. One pivotal figure in resolving these dilemmas was Niels Bohr, a distinguished physicist from Denmark. In 1913, he introduced a revolutionary concept. Electrons are not randomly distributed, but instead occupy quantized orbits at specific distances from the nucleus. Bohr proposed that these distances represented energy levels, with electrons unable to exist closer than a minimum allowable distance from the nucleus. This groundbreaking idea laid the groundwork for a deeper understanding of atomic structure and resolved many perplexing questions about electron behavior. Bohr's model drew heavily on the earlier work of Max Planck, who, in the early 20th century, introduced the concept of quantization in the context of radiation emission. Planck's insights revealed that radiation could only be emitted or absorbed in discrete amounts, determined by a constant value known as Planck's constant. Bohr adapted this principle, asserting that the smallest orbit an electron could have corresponded to 1 unit of angular momentum, quantified by Planck's constant. Larger orbits were multiples of this fundamental unit, but fractions such as 1.3 or 2.6 were not possible. This precise quantization reconciled many issues in atomic theory. To understand how quantum mechanics transformed our view of electron behavior, we must first consider the classical model of the atom. Before quantum theory emerged, electrons were thought of as tiny particles orbiting the nucleus in much the same way that planets orbit the sun. However, this model presented a fundamental problem. According to classical physics, charged particles like electrons would emit electromagnetic radiation while accelerating along curved paths. This radiation would cause them to lose energy, spiral inward, and eventually collapse into the nucleus. Clearly, this did not happen in reality, as atoms were known to be stable structures. Quantum mechanics introduced a groundbreaking concept to resolve this paradox: the wave-particle duality of electrons. This principle posits that electrons, while often behaving like particles, can also exhibit wave-like properties. This duality was demonstrated in experiments such as the double-slit experiment, which showed that electrons could produce interference patterns characteristic of waves. This revelation fundamentally changed our understanding of atomic structure. The wave-like nature of electrons implies that they do not move along well-defined orbits as classical particles would. Instead, they form standing wave patterns around the nucleus. These standing waves, much like the harmonics on a guitar string, are confined to specific wavelengths that fit perfectly within the spatial constraints of the atomic structure. Just as a guitar string vibrates only at certain frequencies to produce distinct notes, an electron's wave can only exist at certain energy levels, leading to discrete and stable configurations. The nearest electron orbit corresponds to the first standing wave, representing the simplest harmonic. In this state, the electron's wave has the smallest possible wavelength that fits around the nucleus. Higher energy orbits correspond to additional harmonics, where the electron wave forms more complex patterns with greater numbers of nodes. Each harmonic represents a specific energy level, and electrons can only occupy these quantized energy states. This restriction is a direct consequence of quantum mechanics and ensures the stability of atoms. Mathematically, the behavior of electron waves is described by Schrödinger's equation, a foundational principle of quantum mechanics. This equation predicts the probability distribution of an electron's position around the nucleus, known as an electron cloud. Instead of envisioning electrons as particles following precise paths, quantum mechanics presents them as probabilities spread over space. This probabilistic nature reflects the uncertainty inherent in quantum systems, encapsulated by Heisenberg's uncertainty principle, which states that one cannot simultaneously know an electron's exact position and momentum. The quantization of energy levels resolves the issue of radiation emission predicted by classical physics. In the quantum model, electrons do not radiate energy as long as they remain within a specific energy state. Energy is only absorbed or emitted when an electron transitions between these states, corresponding to a change in its standing wave pattern. These transitions occur in discrete packets of energy, or quanta, aligning with the observations of atomic spectra. The Bohr model, an early attempt to describe atomic structure, incorporated some of these quantum ideas. Niels Bohr proposed that electrons could only occupy specific orbits, with the angular momentum of each orbit quantized. Although Bohr's model was a significant step forward, it was later refined by the full framework of quantum mechanics, which provided a more accurate and comprehensive description. One of the key insights from quantum mechanics is the relationship between the wave-like nature of electrons and their energy levels. The energy of an electron is inversely proportional to the square of its wavelength. Consequently, electrons in higher energy states corresponding to larger wavelengths are farther from the nucleus. This relationship explains why electrons cannot occupy arbitrary positions or energy levels. Their wave properties impose strict constraints on their behavior. The standing wave patterns also help explain the arrangement of electrons in different atomic orbitals. Electrons in the same energy level occupy regions of space defined by their wave functions. These orbitals have distinct shapes and orientations, such as spherical s orbitals or dumbbell-shaped p orbitals. The distribution of electrons in these orbitals determines an atom's chemical properties, including how it interacts with other atoms to form molecules. Quantum mechanics also provides insights into the stability of atoms. In classical physics, the attraction between the positively charged nucleus and the negatively charged electrons should cause the electrons to collapse into the nucleus. However, quantum mechanics prevents this collapse by imposing a minimum energy level for the electrons, corresponding to the first harmonic or ground state. This energy barrier ensures that electrons remain in stable configurations, maintaining the integrity of the atom. The implications of wave-particle duality extend beyond atomic structure. This concept has profound applications in understanding chemical bonding, spectroscopy, and even modern technologies such as semiconductors and quantum computing. By viewing electrons as waves, scientists can predict the behavior of atoms and molecules with remarkable precision, enabling advancements in fields ranging from materials science to medicine. Quantum mechanics revolutionized our understanding of electrons by revealing their dual nature as particles and waves. This wave-particle duality led to the discovery of standing wave patterns that define electron energy levels and atomic structure. These insights resolved long-standing paradoxes in classical physics, providing a stable and predictive model of the atom. The elegance of this quantum framework continues to inspire scientific exploration, highlighting the profound connections between the microscopic world of particles and the macroscopic universe. Quantum mechanics provides a revolutionary explanation for the stability of atoms, which had long puzzled scientists. In classical physics, the behavior of an electron orbiting a nucleus was likened to a planet revolving around the sun, governed by the principles of electromagnetism and Newtonian mechanics. According to this classical view, electrons, which are negatively charged, would be attracted to the positively charged nucleus, and as they orbited, they would continuously radiate electromagnetic energy. This radiation would cause the electron to lose energy, causing its orbit to decay, ultimately leading to the electron spiraling inward and collapsing into the nucleus. This classical prediction, however, did not match observations, as atoms were stable and did not collapse under the influence of their electromagnetic forces. The key to resolving this paradox lay in the advent of quantum mechanics, which introduced new principles that fundamentally changed our understanding of atomic structure. Quantum mechanics imposed a set of strict rules on the behavior of particles at microscopic scales, including the behavior of electrons in atoms. According to quantum theory, electrons are not confined to specific paths or orbits as classical physics would suggest. Instead, they exist in quantized energy levels. These energy levels are discrete, meaning that the electrons can only occupy certain allowed states with specific amounts of energy. This quantization of energy is essential to the stability of the atom. Rather than spiraling inward due to electromagnetic attraction, electrons occupy these distinct orbits, or energy levels, around the nucleus. For an electron to move from one orbit to another, it must absorb or emit a precise amount of energy corresponding to the difference between the two levels. This restriction on the possible orbits and energy states available to the electron means that, under normal circumstances, an electron cannot spiral into the nucleus. In other words, quantum mechanics introduced the idea of stable electron orbits, where the electron's energy is in equilibrium with the forces acting on it. The key to this stability lies in the delicate balance between the kinetic energy of the electron and the electric force pulling it toward the nucleus. As an electron moves in its orbit, its kinetic energy, the energy associated with its motion, balances the potential energy created by the electrostatic attraction between the negatively charged electron and the positively charged nucleus. This creates a stable energy equilibrium in which the electron neither loses energy by radiating nor gains enough energy to escape from its orbit. Essentially, quantum mechanics ensures that the electron is confined to its orbit, preventing it from spiraling inward or escaping the atom. Later, quantum mechanics developed further, and the full explanation of electron behavior came with the Schrödinger equation and the Heisenberg uncertainty principle. The Schrödinger equation describes the wave-like behavior of electrons, meaning that electrons are not just particles moving in specific paths, but rather exhibit wave-particle duality, existing in a probability distribution rather than following a defined orbit. The Heisenberg uncertainty principle, on the other hand, states that the position and momentum of a particle like an electron cannot be simultaneously known with infinite precision. This fundamentally changed the way we think about the behavior of electrons, further supporting the idea that electrons do not follow fixed paths, but are instead described by probability clouds or orbitals. The quantization of energy and the concept of stable orbits form the cornerstone of atomic stability. Without this quantum mechanical framework, atoms would be unstable, as electrons would continuously radiate energy and collapse into the nucleus. Instead, quantum mechanics imposes a strict order on the energy levels of electrons, ensuring that atoms remain stable and can persist indefinitely, barring any external disturbances. This stability is essential for the existence of matter as we know it. In addition to the stability of individual atoms, the principles of quantum mechanics also explain the chemical behavior of elements. The arrangement of electrons in atomic orbitals, dictated by quantum mechanics, determines how atoms interact with each other and form bonds. The outermost electrons of an atom, often referred to as valence electrons, are primarily responsible for chemical reactions. The specific arrangement of these electrons in discrete energy levels dictates how atoms bond with one another to form molecules, giving rise to the vast array of chemical substances and materials that make up the universe. The stability of atoms, governed by quantum mechanics, thus lays the foundation for the structure and behavior of all matter in the universe. Without the quantum mechanical restrictions on electron energy levels, the delicate balance of forces within atoms would be disrupted, and the universe would be a very different place. Instead, quantum mechanics ensures that atoms are stable, persistent entities, forming the fundamental building blocks for everything from simple elements to complex organic molecules, and enabling the formation of stars, planets, and even life itself. The explanation provided by quantum mechanics for the stability of atoms revolutionized our understanding of the microscopic world. Classical physics had predicted that electrons should spiral inward into the nucleus, causing atoms to collapse, but quantum mechanics introduced the concept of quantized energy levels, which prevents this collapse. Electrons occupy stable orbits, with their kinetic energy balanced by the electric pull of the nucleus. This energy equilibrium ensures that atoms remain stable and do not collapse, forming the cornerstone of all matter in the universe. Through the combined efforts of pioneering scientists and the revolutionary framework of quantum mechanics, the atom's enigmatic nature began to unfold. These discoveries not only illuminated the intricate dance of electrons around the nucleus, but also provided profound insights into the fundamental forces shaping the universe. The formation of atoms, the fundamental building blocks of matter, is intricately tied to the universe's earliest moments. The Big Bang Theory, first formulated in the early 20th century, offers a profound explanation of this process. According to this theory, the universe began as a singularity, a state of infinite density and temperature, approximately 13.8 billion years ago. This singularity experienced a monumental expansion event, commonly referred to as the Big Bang, setting the stage for the formation of atoms and the complex structures we observe today. The standard model of cosmology provides a framework for understanding this cosmic narrative, tracing the universe's evolution back to its singular origin. By examining the universe's expansion and the cosmic microwave background radiation, scientists have established a timeline of pivotal epochs, each contributing to the eventual formation of atoms. Following inflation, the universe entered the quark epoch, a period dominated by an intense soup of quarks and gluons. Temperatures during this phase reached approximately 1015 Kelvin, high enough to prevent quarks from forming stable particles. However, as the universe continued to cool, quarks began to coalesce, giving rise to composite particles such as protons and neutrons. These developments marked the beginning of the formation of matter as we know it. During the earliest phases of the universe, particle-antiparticle pairs were constantly being created and annihilated in a highly dynamic equilibrium. For every particle of matter, there was an equivalent antiparticle, leading to a balance between matter and antimatter. This balance meant that the universe consisted primarily of pure energy, with very little net matter. If this equilibrium had remained undisturbed, the annihilation of particles and antiparticles would have continued indefinitely, leaving behind a universe consisting mostly of radiation, with very little matter to form stars, planets, and galaxies. The annihilation process is relatively straightforward. When a particle and its antiparticle come into contact, their masses are converted into energy, typically in the form of high-energy photons. For example, when an electron and a positron meet, they annihilate to produce two photons, which carry away the energy. In this process, the total mass energy of the system is conserved, meaning that the mass of the particles is entirely converted into radiation. This process is highly efficient, ensuring that almost all particles of matter and antimatter would have been annihilated under normal conditions. However, there is a crucial detail that distinguishes the fate of the universe: a subtle asymmetry in the behavior of matter and antimatter. This asymmetry is often referred to as the matter-antimatter asymmetry, or the baryon asymmetry. In the early universe, for reasons that are still not fully understood, the annihilation of particles and antiparticles did not happen in perfect balance. For every billion annihilations that took place, a tiny fraction of matter particles managed to survive. This slight excess of matter over antimatter left behind the residual matter that forms the universe we know today. This imbalance, although extremely small, on the order of one extra particle of matter for every billion particle-antiparticle pairs, was crucial. Without this surplus, the annihilation process would have wiped out all matter, leaving behind only radiation and no substance from which stars, galaxies, and eventually life could form. The key to understanding this process lies in the fact that the remaining matter particles, after the majority of matter-antimatter pairs annihilated each other, formed the building blocks of everything in the universe. Without the asymmetry, there would be no matter to create the structures we observe today. The cause of this asymmetry is still a subject of intense research. One of the proposed explanations is a phenomenon known as CP violation, where the laws of physics exhibit a preference for certain processes involving particles and their antiparticles over others. In particular, CP violation refers to the idea that the universe behaves differently when matter and antimatter are swapped, C symmetry, or when time is reversed, P symmetry. The discovery of CP violation in certain particle interactions, such as those involving the weak force, responsible for processes like radioactive decay, has provided some insight into how this slight imbalance could arise. In the context of the early universe, CP violation would have resulted in a tiny but significant difference in the interactions of matter and antimatter. As a result, after a series of particle interactions, a small excess of matter particles was left behind, while the majority of antimatter particles annihilated with their corresponding matter particles. This excess of matter provided the foundation for the creation of the observable universe. Once the matter particles had survived the annihilation process, the remaining universe was composed mostly of radiation, with a small but crucial amount of matter. Over time, as the universe cooled and expanded, the surviving particles began to clump together due to gravitational attraction, forming the first atoms and, later, the first stars and galaxies. The presence of matter, though minuscule in comparison to the radiation, became the seed for all the structures that make up the universe today. The matter-antimatter asymmetry has profound implications not just for cosmology, but also for the very existence of life itself. If the balance between matter and antimatter had been perfect, there would be no matter to form the stars, planets, and galaxies that make up the cosmos. There would be no elements to form molecules, no atoms to create the chemistry necessary for life. The very possibility of life as we know it hinges on this subtle imbalance in the early universe. Without this slight excess of matter, the conditions necessary for the formation of planets and stars would never have existed, and the complex processes leading to the emergence of life would not have occurred. This process is often referred to as one of the fine-tuning aspects of the universe, where a seemingly trivial difference in conditions has led to a universe that is hospitable to life. The exact mechanisms behind this asymmetry remain one of the most profound mysteries in physics and cosmology. Several theories have been proposed, ranging from extensions of the standard model of particle physics to new concepts in cosmology, but no single explanation has yet been universally accepted. The annihilation of particles and their antiparticles played a central role in shaping the universe as we know it. While matter and antimatter existed in near equal amounts in the early universe, a slight asymmetry allowed a small excess of matter to survive the annihilation process. This surplus of matter formed the foundation for the universe's structure, enabling the creation of stars, galaxies, and the conditions necessary for life. The discovery and study of the matter-antimatter asymmetry remain one of the most exciting and challenging areas of modern physics, as it holds the key to understanding the fundamental nature of the universe and the origins of everything within it. Around 3 minutes after the Big Bang, the universe entered a phase known as Big Bang nucleosynthesis, BBN. During this epoch, protons and neutrons combined to form the first atomic nuclei, primarily hydrogen and helium. This process was governed by the rapidly cooling temperatures, which allowed nuclei to form while preventing further particle collisions that could disrupt these newly formed structures. By the end of BBN, the universe's matter was composed of approximately 75% hydrogen nuclei and 25% helium nuclei, with trace amounts of other light elements such as lithium and deuterium. Following nucleosynthesis, the universe transitioned into the photon epoch, which lasted until approximately 380,000 years after the Big Bang. During this period, the universe was dominated by a plasma of ionized nuclei and electrons, preventing photons from traveling freely. The intense interactions between photons and charged particles rendered the universe opaque, resembling a dense fog. As the universe continued to cool, it reached a critical temperature of approximately 3000 Kelvin, enabling a transformative event known as recombination. During recombination, electrons began to combine with nuclei to form neutral atoms, primarily hydrogen and helium. This process drastically reduced the number of free electrons, allowing photons to travel unimpeded for the first time. The liberation of these photons marked the beginning of the cosmic microwave background, CMB radiation, a faint glow that permeates the universe and serves as a relic of its early history. The CMB provides a snapshot of the universe at the moment of recombination, offering invaluable insights into its initial conditions and subsequent evolution. By studying the slight temperature fluctuations in the CMB, scientists have been able to infer the distribution of matter and energy in the early universe, as well as the seeds of the large-scale cosmic structures observed today. The intricate interplay of high-energy physics, quantum mechanics, and cosmological dynamics during these epochs underscores the complexity of the atom formation process. From the intense quark-gluon plasma of the quark epoch to the serene release of the cosmic microwave background, the story of atom formation is a testament to the universe's capacity for transformation and complexity. Each epoch, with its distinct physical conditions and processes, played a crucial role in shaping the matter that constitutes everything from the smallest particles to the grandest galaxies. The fascinating interplay of forces and principles at the atomic level lays the foundation for the intricate structures and behaviors of matter in the universe. Atoms rarely exist in isolation. Instead, they interact with one another through various mechanisms, forming molecules and complex compounds. These interactions are governed by fundamental forces and the quest for stability within the realm of quantum mechanics. At the heart of atomic interactions lies the electromagnetic force, a pivotal factor in the behavior of electrons and protons. Electrons, negatively charged particles, are bound to the positively charged nucleus by this force, creating the stable structure of an atom. When atoms come into proximity, their electron clouds interact, resulting in a variety of outcomes depending on the nature of the forces involved. For example, repulsive forces between negatively charged electrons can prevent atoms from collapsing into each other, while attractive forces between opposite charges enable the formation of bonds. An additional force, known as the van der Waals force, plays a subtle yet crucial role in the interaction between atoms and molecules. Unlike the stronger electromagnetic force, van der Waals forces arise from temporary fluctuations in charge distribution within atoms or molecules. These transient dipoles create weak attractions between particles, facilitating the assembly of molecular structures. Although these forces are relatively weak compared to covalent or ionic bonds, they are essential in phenomena such as protein folding, the cohesion of liquids, and the behavior of noble gases at low temperatures. The process of chemical bonding is a cornerstone of molecular formation. Two primary types of bonds, covalent bonds and ionic bonds, dominate this domain. In a covalent bond, atoms share one or more pairs of electrons to achieve a stable configuration, effectively completing their valence shells. This sharing results in strong, stable molecules such as water, H2O, and carbon dioxide, CO2. In contrast, an ionic bond forms when one atom transfers electrons to another, creating ions with opposite charges that attract each other. Examples include sodium chloride, NaCl, where sodium donates an electron to chlorine, leading to the formation of a crystal lattice. The driving force behind chemical bonding is rooted in the principle of energy minimization. a fundamental concept that explains why atoms interact and form compounds. Just as a marble seeks the lowest point when rolled down a hill, atoms naturally tend to arrange themselves in ways that reduce their potential energy. This drive towards energy reduction is what underpins the formation of chemical bonds and the creation of a wide variety of substances in nature. At the atomic level, energy plays a central role in determining the behavior of particles. Atoms consist of a nucleus, made up of protons and neutrons, surrounded by electrons that orbit in distinct energy levels or shells. The arrangement of these electrons, particularly the valence electrons, those in the outermost shell, governs an atom's chemical reactivity. When atoms interact, their goal is to reach a configuration that minimizes the system's total energy. This is the essence of chemical bonding. When atoms bond, they either share or transfer electrons, creating a more stable arrangement. The most common types of chemical bonds are covalent and ionic bonds. In a covalent bond, atoms share electrons, and in an ionic bond, electrons are transferred from one atom to another. In both cases, the result is a more stable configuration compared to the isolated atoms. The reason atoms are motivated to bond is that on their own, they often possess relatively high potential energy. This is because their outermost electron shells are not always full, and an incomplete shell corresponds to an unstable arrangement. Atoms are most stable when their electron shells are full, particularly the valence shell. This is in accordance with the octet rule, which states that atoms tend to form bonds in such a way that they achieve 8 electrons in their valence shell, which mirrors the electron configuration of noble gases, known for their chemical stability. For example, the hydrogen atom has 1 electron in its outermost shell and seeks another electron to fill its shell, making it more stable. This is why hydrogen atoms bond with other hydrogen atoms, forming a H2 molecule by sharing electrons. Similarly, oxygen atoms, which have 6 valence electrons, will bond with 2 hydrogen atoms to form H2O, a highly stable molecule. In these cases, by sharing electrons, atoms reduce their energy and achieve a more stable, energetically favorable state. In ionic bonding, energy minimization occurs through the transfer of electrons. This typically happens between atoms with very different electronegativities, such as sodium, Na, and chlorine, Cl. Sodium, with 1 electron in its outer shell, is eager to lose that electron to achieve a stable configuration. Chlorine, on the other hand, has 7 electrons in its valence shell and seeks to gain 1 more to complete its octet. When sodium donates an electron to chlorine, both atoms become more stable. Sodium becomes a positively charged ion, Na+, and chlorine becomes a negatively charged ion, Clr. These oppositely charged ions are strongly attracted to each other, forming an ionic bond. The energy released during the formation of this bond stabilizes the resulting compound, sodium chloride, NaCl. The process of forming bonds is also influenced by electronegativity, a measure of an atom's ability to attract and hold on to electrons. In a covalent bond, when 2 atoms have a similar electronegativity, they share electrons equally, as seen in molecules like O2 or N2. However, when there is a significant difference in electronegativity between 2 atoms, one atom attracts the shared electrons more strongly, leading to a polar covalent bond. For instance, in a water molecule, H2O, oxygen is more electronegative than hydrogen, so the shared electrons spend more time around the oxygen atom, creating partial positive charges on the hydrogen atoms and a partial negative charge on the oxygen atom. In addition to reducing potential energy, the formation of chemical bonds results in the release of energy. This energy release is typically in the form of heat or light. When bonds form, the atoms or molecules involved reach a more stable state, and the energy required to hold them together is less than the energy they originally had. This is why the formation of chemical bonds is often exothermic, meaning that energy is released during the process. For example, when carbon atoms bond with hydrogen atoms to form methane, CH4, energy is released. The bond between carbon and hydrogen in methane is stable, and the formation of the molecule results in a net release of energy. This energy release is crucial in various natural processes, including the burning of fuels. The combustion of methane, for instance, involves breaking the bonds of methane molecules and forming bonds with oxygen to produce carbon dioxide, CO2, and water, H2O, with the release of heat and light. In contrast, breaking bonds requires energy input. When atoms are separated, or when chemical bonds are broken, energy must be supplied to overcome the forces holding the atoms together. This is why endothermic reactions, like the decomposition of water into hydrogen and oxygen gases, require an external energy source, such as heat or electricity, to drive the reaction. In addition to the direct energy changes associated with bond formation, chemical bonding also plays a role in determining the properties of substances. The type of bond and the way atoms arrange themselves in a molecule or compound directly influence the material's physical properties, such as its melting point, boiling point, hardness, conductivity, and solubility. For example, the ionic bonds in sodium chloride give it a high melting point and make it an excellent conductor when dissolved in water. On the other hand, the covalent bonds in diamond give it extreme hardness, while the covalent bonds in graphite allow the layers of atoms to slide over each other, making it soft and a good conductor of electricity. The fundamental process of energy minimization through bonding not only dictates the stability of molecules and compounds, but also the vast array of substances that exist in nature. Without the ability of atoms to bond in various ways, the complexity of the molecular world would not exist. The diversity of substances found in nature, from the simplest molecules like oxygen, O2, to complex biological molecules such as proteins, DNA, and enzymes, all arises from the interactions between atoms seeking stable, low-energy configurations. The principle of energy minimization is the core reason atoms bond to form stable structures. By sharing or transferring electrons, atoms achieve more stable, lower-energy configurations, which is energetically favorable. Whether through covalent or ionic bonding, these interactions lead to the formation of a vast array of substances that are not only stable, but also exhibit a variety of physical and chemical properties. This fundamental process of bonding, which drives the formation of matter and its various forms, is essential to the very fabric of the universe and the diverse chemical systems that sustain life. The pursuit of stability through chemical bonding is thus a foundational principle that governs the behavior of atoms and molecules, shaping everything from the simplest elements to the most complex life forms. Molecular diversity arises from several factors that influence atomic interactions and bonding. One such factor is the unique emission spectra of elements. Each element emits or absorbs light at specific wavelengths, creating a distinctive spectral fingerprint. These spectra reflect the unique arrangement of electrons within an atom, influencing how it interacts with other atoms and molecules. For example, the spectral lines of hydrogen differ significantly from those of helium, dictating their bonding behaviors and roles in molecular structures. Quantum mechanics further enriches our understanding of bonding and molecular diversity. The behavior of electrons, governed by the principles of wave-particle duality, plays a pivotal role in determining bond strengths, lengths, and angles. Electrons are not merely particles orbiting the nucleus, but are better described as wave functions distributed in specific regions around the nucleus, known as orbitals. The overlap of these orbitals between atoms determines the nature and strength of the bonds formed. For instance, the sharing of electrons in a covalent bond results from the overlap of atomic orbitals, creating a region of high electron density that binds the nuclei together. The stability of molecules is further influenced by the concept of valence shells. Atoms achieve stability by filling their outermost electron shells, a phenomenon most apparent in noble gases. These elements, such as helium, He, neon, Ni, and argon, Ar, possess naturally complete valence shells, rendering them chemically inert under normal conditions. Their reluctance to form bonds underscores the importance of electron configuration in determining atomic and molecular behavior. In contrast, elements with incomplete valence shells, such as hydrogen, oxygen, and carbon, exhibit a strong propensity to bond, resulting in the formation of complex molecules. Carbon, with its 4 valence electrons, serves as a prime example. Its ability to form up to 4 covalent bonds enables the creation of an immense variety of organic compounds, including those that form the basis of life. The versatility of carbon arises from its capacity to hybridize its orbitals, allowing for single, double, and triple bonds, and the formation of intricate molecular frameworks. The interplay of forces and quantum principles at the atomic scale extends beyond individual bonds to influence the properties and behaviors of macroscopic materials. For instance, the arrangement of atoms within a crystal lattice determines the hardness of diamonds or the conductivity of metals. Similarly, the molecular structure of water, with its hydrogen bonds, accounts for its unique properties, such as high surface tension and its role as a universal solvent. Furthermore, molecular interactions are not static but dynamic, allowing for the formation and breaking of bonds under specific conditions. Chemical reactions, driven by changes in energy and facilitated by catalysts, enable the transformation of molecules into new forms. These processes underpin countless natural and technological phenomena, from the metabolism of glucose in living organisms to the synthesis of pharmaceuticals and materials. The role of atomic interactions in molecular formation extends to the realm of supramolecular chemistry, where weak forces such as hydrogen bonds, van der Waals forces, and pp interactions govern the assembly of complex structures. This field explores how molecules organize themselves into larger architectures, enabling the development of innovative materials and nanotechnology. The principles of atomic interactions and molecular formation not only explain the stability and diversity of matter, but also reveal the underlying unity of the physical world. From the simple hydrogen molecule to the intricate biomolecules essential for life, the same fundamental forces and quantum principles govern their behavior. This profound connection underscores the elegance and complexity of nature, where the interplay of particles and forces creates the boundless diversity of the universe. The stability and variability of atoms are fundamental to understanding the physical universe. Atoms, though minute in size, are extraordinarily complex and are held together by powerful forces. Their components, primarily protons, neutrons, and electrons, interact through these forces to form stable structures, while variations in these components give rise to isotopes and dynamic nuclear reactions. Protons and neutrons are the primary constituents of the atomic nucleus. They are not elementary particles, but are composed of smaller particles called quarks, which are bound together by gluons. Gluons act as carriers of the strong nuclear force, one of the 4 fundamental forces of nature. This force is immensely powerful at short distances and is responsible for binding quarks to form protons and neutrons, and subsequently holding protons and neutrons together within the nucleus. Without the strong nuclear force, atomic nuclei would disintegrate due to the electromagnetic repulsion between positively charged protons. The strong nuclear force is one of the fundamental forces of nature, and its behavior is indeed unique compared to the other forces, such as gravity or electromagnetism. At the heart of the strong nuclear force is its role in holding the basic building blocks of matter, namely quarks, together to form protons and neutrons. Quarks are elementary particles that combine in groups of 3 to form these baryons, protons and neutrons, and the strong nuclear force is responsible for keeping them confined within these particles. The way this force behaves is often described as being similar to a stretched elastic band. When quarks are pulled apart within a proton or neutron, the strong nuclear force actually increases in strength the further they are separated, unlike other forces that typically weaken over distance. This property is a key characteristic of the strong nuclear force, and it ensures that quarks remain bound together inside the nucleus. As quarks are pulled apart, the strong force becomes stronger, pulling them back together with an intensity that prevents them from escaping. This characteristic, often referred to as asymptotic freedom, essentially keeps quarks confined within hadrons, protons, neutrons, and other particles made up of quarks. This behavior of the strong force can be likened to the stretching of an elastic band. When you pull the band further, it resists with greater force. However, as you keep pulling the band to the point where it becomes too stretched, the force of resistance eventually leads to a breaking point. Similarly, as quarks are pulled farther apart, the energy required to continue separating them increases. If this energy exceeds a certain threshold, the quarks do not simply escape freely, but instead cause the creation of new particles in a process called quark confinement. Thus, quarks cannot exist independently and are forever confined within larger composite particles such as protons and neutrons. Beyond the individual nucleons, protons and neutrons, the residual effects of the strong nuclear force extend further, helping to bind the nucleus together. This is known as the nuclear binding force. The nuclear binding force is the interaction between the nucleons, protons and neutrons, that holds the nucleus of an atom together. The force is much weaker than the strong force that binds quarks inside protons and neutrons, but is still incredibly strong when considering the small distances within an atomic nucleus. This force is what prevents the positively charged protons from repelling each other due to their electromagnetic interactions. Without the nuclear binding force, the nucleus would disintegrate, as the electromagnetic repulsion between protons would overpower the forces keeping the nucleons together. The strength of the strong nuclear force ensures that atomic nuclei are stable under normal conditions. However, the force's strength is also responsible for the processes of nuclear fusion and fission. In fusion, lighter nuclei, such as hydrogen, come together to form heavier nuclei, releasing vast amounts of energy in the process. In fission, heavy nuclei, like uranium, split into smaller nuclei, also releasing a large amount of energy. These processes rely on the balance between the strong nuclear force and the electromagnetic force, with the strong force providing the necessary attraction to keep the nucleus intact, while electromagnetic forces can disrupt the nucleus if conditions are right. The strong nuclear force is also responsible for much of the energy produced in stars. In the core of stars, the immense gravitational pressure causes atoms to undergo nuclear fusion, converting light elements into heavier elements. This intricate balance between forces within the nucleus is fundamental not only for the stability of matter, but also for the processes that fuel the universe. Whether in the core of a star or in the laboratory in controlled nuclear reactions, the strong nuclear force governs how matter behaves on a subatomic level. It ensures that quarks remain confined within protons and neutrons, maintains the integrity of atomic nuclei, and drives the fundamental processes of nuclear fusion and fission that power stars and shape the evolution of elements in the universe. The strong nuclear force exhibits a unique and fascinating behavior, where it strengthens as quarks are separated, ensuring that they remain confined within protons and neutrons. This force's effects extend to a larger scale, creating the nuclear binding force that holds atomic nuclei together. It is the foundation of the stability of matter, enabling the creation of the elements and driving the processes that govern the life cycle of stars and the formation of the universe itself. The variability of atoms is most evident in their isotopes, which are variants of the same element with differing numbers of neutrons. While the proton number, or atomic number, defines the identity of an element, variations in neutron numbers result in isotopes with differing mass numbers. For instance, hydrogen has 3 isotopes: protium, no neutrons; deuterium, 1 neutron; and tritium, 2 neutrons. Isotopes of the same element exhibit nearly identical chemical behavior, but can differ significantly in nuclear properties. The applications of isotopes are vast and transformative. Carbon-14, an isotope of carbon, is integral to radiocarbon dating, a technique used to determine the age of archaeological and geological samples. Carbon-14 decays over time with a known half-life of approximately 5,730 years, allowing scientists to calculate the age of organic materials. Similarly, isotopes like uranium-235 and plutonium-239 are pivotal in nuclear energy and weaponry due to their capacity to undergo fission reactions, releasing immense amounts of energy. The concept of radioactive decay highlights the variability and transience of certain isotopes. Unstable isotopes undergo decay, transforming into different elements or isotopes while emitting radiation. This decay occurs in distinct modes, including alpha decay, beta decay, and gamma decay, each involving the emission of specific particles or energy. If proton decay were confirmed, it would have profound implications for our understanding of matter and the universe's long-term future. Over trillions of years, the gradual decay of protons would lead to the disintegration of all atomic matter, leaving behind a universe dominated by radiation and elementary particles. However, despite extensive searches, proton decay remains undetected, and its existence is purely theoretical at present. The stability and variability of atoms are direct consequences of the intricate balance of forces and interactions at the subatomic level. The way atoms behave, how they remain intact or undergo transformation, is dictated by a combination of the strong nuclear force, the electromagnetic force, and the principles of quantum mechanics. These fundamental interactions shape the structure and behavior of atoms, ensuring their persistence in stable configurations, while also allowing them to engage in dynamic transformations like chemical reactions and nuclear processes. This duality, where atoms maintain their structure yet are capable of undergoing change, reveals the complexity and elegance of the atomic world. The strong nuclear force is one of the most powerful forces in nature, operating at very short distances, typically within the nucleus of an atom. It is responsible for binding protons and neutrons together, overcoming the electromagnetic repulsion between positively charged protons. Without the strong nuclear force, atomic nuclei would not exist, and the universe would be devoid of the rich variety of elements that constitute matter. This force is crucial to the stability of atomic nuclei, as it ensures that despite the repulsive force between positively charged protons, the nucleus remains intact. The strong nuclear force thus provides the foundation for the persistence of atoms and the elements they form. In contrast, the electromagnetic force plays a central role in determining the behavior of atoms on a larger scale. This force governs the interactions between charged particles, including the electrons that orbit the nucleus. Electrons, being negatively charged, are attracted to the positively charged nucleus, and this attraction holds them in their respective energy levels, or shells. The electromagnetic force also governs the interactions between atoms themselves, determining the way atoms bond to form molecules. Covalent bonds, for example, occur when atoms share electrons to achieve a more stable configuration, while ionic bonds form when electrons are transferred between atoms, creating oppositely charged ions that are held together by electromagnetic attraction. Quantum mechanics, a framework that describes the behavior of particles at the smallest scales, introduces another layer of complexity to the atomic world. Quantum theory dictates that particles, such as electrons, do not have definite positions or velocities until measured. Instead, they exist in a state of probability, represented by wave functions that describe the likelihood of finding an electron in a particular region around the nucleus. This probabilistic nature of quantum mechanics means that the exact behavior of electrons cannot be predicted with certainty, only in terms of probabilities. As a result, atomic orbitals are not simply paths that electrons follow, but rather regions in space where electrons are likely to be found. This introduces an element of variability to atomic behavior, as the precise arrangement of electrons within an atom can change in response to external factors like energy input or the presence of other atoms. The Heisenberg uncertainty principle, a core concept in quantum mechanics, further emphasizes the duality of stability and change. it states that we cannot simultaneously know both the position and the momentum of a particle with complete certainty. This limitation in measurement does not affect the stability of atoms in their typical state, but does allow for dynamic changes when atoms interact with external forces or other atoms. For example, when atoms absorb or emit energy in the form of photons, their electrons can jump between different energy levels, leading to changes in their configuration and behavior. Such changes are governed by the probabilistic nature of quantum mechanics, reflecting the variability of atomic behavior. While the forces at play within atoms work to maintain their stability, they also allow for transformation and variability. For instance, when atoms are subjected to high energy conditions, such as in chemical reactions or nuclear reactions, they can undergo processes that alter their structure. In a chemical reaction, atoms may form new bonds or break existing ones, resulting in the creation of new molecules. Similarly, in nuclear reactions, the nucleus of an atom can undergo fission or fusion, releasing large amounts of energy and transforming the elements involved. The balance between stability and variability is central to the formation of the diverse array of matter found in the universe. The periodic table of elements reflects the different ways atoms can combine, each element with its own unique set of properties governed by its atomic structure. The differences in atomic configurations lead to the creation of various materials, from the simplest gases like hydrogen and helium to more complex substances like carbon-based life forms. The versatility of atoms in forming different molecules, combined with the stability that allows these molecules to persist over time, is the basis for the vast complexity of the material world. This atomic duality is also a key to the processes that shape our universe. Stars, for example, are formed by the fusion of lighter elements like hydrogen into heavier elements like helium, releasing immense amounts of energy. These processes, driven by the strong nuclear force, not only create the elements that form the planets and life, but also provide the energy that sustains stars for billions of years. The variability of atoms allows them to undergo these reactions, while their stability ensures the long-term persistence of the structures formed. In the world of chemistry, atoms' ability to form and break bonds underlies the vast array of reactions that take place in nature. Whether in biological systems, where atoms combine to form complex molecules like proteins and DNA, or in geological processes, where atoms form minerals and crystals, the interplay of stability and change at the atomic level is at the core of these transformations. Even the formation of life itself depends on the precise arrangement and interaction of atoms, where stable structures, such as molecules, can undergo dynamic processes, enabling the complex processes that sustain living organisms. In essence, the forces and interactions that govern atomic behavior not only ensure the stability of atoms, but also allow for the variability that drives the transformations seen in the natural world. The strong nuclear force, electromagnetic force, and quantum mechanics combine to create a balance that supports both the persistence of matter and its ability to undergo change. This balance is a testament to the elegance of the atomic world, where stability provides the foundation for the existence of matter, and variability allows for the dynamic processes that shape the universe. Together, they provide the conditions necessary for the formation of the diverse substances we encounter and the dynamic processes that drive the evolution of the universe. The universe, in its vastness and complexity, offers profound connections to the atomic scale, bridging the smallest particles with the grandest cosmic phenomena. One compelling concept is the theory that the universe itself resembles an atom. This perspective emerges from speculative cosmological models and theories, suggesting that the universe's structure and dynamics might mirror those of atomic systems. Some ideas propose that what we perceive as our observable universe could be akin to a single atom within a vastly larger multiverse framework. The multiverse theory further expands this notion by positing the existence of numerous universes, each potentially governed by distinct physical laws and constants. In this context, every universe could represent a fundamental unit in a larger cosmic structure, akin to atoms in a molecule. While these ideas remain speculative, they provoke profound questions about the nature of reality and the universe's place within a possibly infinite multiverse. At a more tangible level, neutron stars serve as remarkable examples of cosmic phenomena that echo atomic structures. Formed through the collapse of massive stars during supernova events, neutron stars are composed almost entirely of densely packed neutrons. The intense gravitational forces at play during the collapse overcome the repulsive forces between protons and electrons, leading to the formation of neutrons through inverse beta decay. The result is an incredibly dense celestial body, with masses up to twice that of the Sun compressed into a radius of merely 10 to 12 kilometers. The behavior of neutron stars is governed by a delicate interplay of forces. Gravity, the dominant force at these scales, attempts to compress the star further. However, the strong nuclear force, which operates at the subatomic level, provides resistance by preventing the neutrons from collapsing entirely. Additionally, the weak nuclear force plays a role in the star's formation and subsequent evolution, particularly during the conversion of protons and electrons into neutrons. This balance of forces results in one of the densest forms of matter in the universe, where a single teaspoon of neutron star material could weigh billions of tons. The study of neutron stars offers insights into fundamental physics, particularly under conditions that cannot be replicated on Earth. Their immense density and unique composition provide a natural laboratory for exploring quantum mechanics, general relativity, and the behavior of matter under extreme conditions. Furthermore, phenomena such as pulsars, rapidly spinning neutron stars emitting beams of electromagnetic radiation, reveal the intricate dynamics of these cosmic entities. The connection between the atomic and cosmic scales, though seemingly vast and unbridgeable, can be found in the underlying forces that shape the universe. One of the most profound examples of this connection is dark energy, an enigmatic and mysterious force responsible for the accelerated expansion of the universe. Despite its massive influence on the cosmos, dark energy remains one of the greatest unsolved puzzles in modern physics. Dark energy accounts for approximately 68% of the total energy content of the universe, yet its nature, properties, and fundamental workings are still largely unknown. In many ways, dark energy's role in the cosmos can be compared to the forces that govern atomic interactions, particularly the forces that bind atomic nuclei. While these forces operate on drastically different scales, atomic and cosmic, the underlying principles that govern the structure and dynamics of matter and the universe share striking similarities. At the atomic scale, the strong nuclear force is the key force responsible for binding protons and neutrons together in the atomic nucleus. This force is extraordinarily powerful, but acts only over a very short range, essentially confined to the size of the nucleus. The strong nuclear force is a fundamental interaction that ensures the stability of atomic nuclei by overcoming the electromagnetic repulsion between positively charged protons. Without this force, atoms could not hold their nuclei together, and the complex chemistry that governs the structure of matter would not exist. This force is critical in shaping the structure of matter on the atomic and subatomic levels. Similarly, at the cosmic scale, dark energy plays a pivotal role in shaping the large-scale structure of the universe. While the strong nuclear force binds the components of an atomic nucleus, dark energy operates on a far grander scale, influencing the expansion of the entire universe. Dark energy's primary effect is to accelerate the expansion of the universe, counteracting the gravitational pull that would otherwise slow it down. It is a force that pushes galaxies apart, increasing the distance between them over time. This expansion is not uniform. It accelerates as the universe ages. Just as the strong nuclear force works to bind the components of an atom together, dark energy works to drive the outward motion of the universe, pushing it apart on the largest scales. The discovery of dark energy was a monumental moment in modern physics. In the late 1990s, astronomers observed that the universe's expansion, rather than slowing down as expected due to the gravitational attraction between galaxies, was actually accelerating. This observation led to the hypothesis that some unknown force was at work, pushing the galaxies apart. After extensive research, scientists determined that this force, which came to be known as dark energy, constitutes the largest portion of the universe's energy content, roughly 68%. This is a stark contrast to the familiar matter that makes up only 5% of the universe, with the remainder being attributed to dark matter, about 27%, which also remains poorly understood. Despite being responsible for the accelerated expansion of the universe, dark energy does not seem to have any observable interaction with matter in the way that gravity or electromagnetism does. Unlike the strong nuclear force, which operates within the confines of an atomic nucleus, dark energy's effects are felt on the cosmic scale, influencing the behavior of entire galaxies and clusters of galaxies. It is a form of energy that is spread throughout space and appears to have a negative pressure that drives the expansion of the universe. This negative pressure is thought to be responsible for the repulsive force that causes the acceleration. In many ways, dark energy can be considered an antithesis to the attractive forces, like gravity, that normally bring matter together. The equation of state for dark energy describes the relationship between its energy density and its pressure. The negative pressure associated with dark energy leads to a repulsive force, pushing galaxies apart. This phenomenon is fundamentally different from gravity, which works to pull matter together. This negative pressure in dark energy is responsible for the observed accelerated expansion of the universe, pushing galaxies farther apart faster as time progresses. The expansion of the universe is not only occurring, but is doing so at an increasing rate due to the overwhelming presence of dark energy. In comparison to atomic forces, where interactions occur on the scale of atoms and subatomic particles, dark energy operates on an incomprehensibly larger scale. The strong nuclear force holds protons and neutrons together within the nucleus of an atom, allowing matter to have form and stability. Similarly, dark energy holds the universe's large-scale structure in a state of dynamic expansion, allowing the universe to persist in its ever-growing state. Just as the strong nuclear force dictates the stability of atomic nuclei, dark energy governs the evolution of the cosmos by ensuring its continual expansion. However, while the strong nuclear force's range is confined to a tiny, subatomic space, dark energy's influence spans the vast, nearly incomprehensible distances between galaxies, affecting the very fabric of space-time itself. One of the fascinating aspects of dark energy is that it is, to date, a mysterious force, one that we do not fully understand. Unlike familiar forces such as gravity and electromagnetism, which have been studied and quantified extensively, dark energy eludes direct observation. Its effects are only visible through the large-scale structure of the universe and the observed acceleration of the expansion. Dark energy does not interact with ordinary matter, nor does it appear to have any electromagnetic radiation that would make it detectable through traditional means. The fact that it is so pervasive yet invisible has made it one of the most intriguing and puzzling aspects of modern cosmology. Various theories have been proposed to explain the nature of dark energy. One possibility is that dark energy is a property of empty space itself, known as the vacuum energy. In this theory, even in a perfect vacuum, there would be a certain amount of energy associated with the very fabric of space. This energy would exert a repulsive force, pushing space itself apart. Another theory suggests that dark energy could be related to a field, much like the Higgs field that gives particles their mass. Theoretical models such as quantum field theory and general relativity offer different perspectives on what dark energy might be, but no definitive explanation has been found. The interplay between dark energy and other cosmic forces, such as gravity, is a central topic in cosmological research. While gravity works to pull matter together, dark energy works in opposition, pushing galaxies apart. The balance between these forces determines the ultimate fate of the universe. If dark energy continues to dominate the expansion of the universe, the cosmos could continue expanding at an accelerating rate, leading to a future where galaxies are so far apart that the observable universe becomes isolated, with each galaxy effectively becoming unreachable. On the other hand, if gravity were to ultimately overpower dark energy, the universe could experience a big crunch, where the expansion reverses and matter collapses back in on itself. The connection between atomic forces and cosmic forces is not just a matter of scale, but also of fundamental principles. Both the strong nuclear force that binds protons and neutrons in atomic nuclei and dark energy's role in the accelerated expansion of the universe operate under the same principle of energy and force interactions. At the atomic level, forces act to bind particles together, creating stability and structure. At the cosmic level, dark energy exerts a force that drives the expansion of the universe, shaping the universe's large-scale structure and ultimately determining its long-term fate. The study of dark energy is central to our understanding of the universe. As we continue to observe the acceleration of the universe's expansion and develop more advanced tools for studying cosmic phenomena, we may uncover more about the true nature of dark energy. Its role in the cosmic evolution of the universe mirrors the role of fundamental forces like the strong nuclear force in atomic systems, underscoring the profound connection between the atomic and cosmic realms. Both realms operate under the guidance of unseen forces that shape the structure, behavior, and ultimate destiny of matter, from the smallest particles to the vastest galaxies. The exploration of dark energy represents a step toward a deeper understanding of the cosmos, bridging the gap between the microscopic and the macroscopic, and highlighting the unity of forces that govern the entire universe. Theoretical frameworks like string theory attempt to bridge these scales by describing the universe's fundamental constituents as tiny, vibrating strings of energy. In this model, atoms and subatomic particles are not point-like entities, but instead arise from the vibrational states of these strings. String theory also suggests the existence of additional dimensions beyond the familiar 3 spatial and 1 temporal dimension, potentially providing a context for understanding dark energy. One speculative model within string theory proposes that our universe resides on the surface of a cosmic brain, a multidimensional structure within a higher dimensional space. According to this view, dark energy could be a manifestation of interactions between our brain and the surrounding multidimensional environment. This idea opens new avenues for exploring the connections between quantum mechanics, cosmology, and the enigmatic forces shaping the universe. Despite their speculative nature, these theories highlight the deep interconnections between the atomic and cosmic realms. From the dense matter of neutron stars to the expansive reach of dark energy, the universe's behavior reflects principles that govern both the smallest particles and the largest structures. These connections underscore the unity of physical laws across scales, revealing a cosmos where the interplay of forces and particles creates an intricate tapestry of existence. Atoms are the silent witnesses to the dynamic processes of life and death, participating in cycles that span biological, geological, and cosmic scales. Their journey begins in the intricate structure of living organisms, extends through the transformative processes of decay and recycling, and ventures into the vast reaches of the cosmos. In life, atoms form the essential building blocks of the human body, which is composed of approximately 60% water, 20% fat, 15% proteins, and various other elements. Key atoms like carbon, hydrogen, oxygen, and nitrogen constitute these compounds, creating the molecules that sustain biological functions. These atoms partake in a molecular cycle, continuously exchanging between the environment and living systems through processes like respiration, digestion, and photosynthesis. When life ends, the journey of atoms enters a new phase. The decomposition process, driven by trillions of bacteria and other microorganisms, begins the transformation of organic matter. These organisms break down proteins, fats, and carbohydrates into simpler compounds. As tissues degrade, gases such as carbon dioxide, methane, and ammonia are released into the atmosphere, contributing to the nutrient cycles of ecosystems. Additionally, atoms from the body seep into the soil, enriching it with essential nutrients like nitrogen, phosphorus, and potassium. These nutrients are absorbed by plants, continuing the cycle of life. The post-mortem journey of atoms extends beyond terrestrial ecosystems. Gases released during decomposition rise into the atmosphere and eventually disperse globally. Some atoms find their way into oceans, rivers, or lakes, integrating into aquatic ecosystems. Others may settle into geological formations, becoming part of the Earth's crust over millennia. Atoms that escape Earth's bounds embark on a cosmic odyssey. Solar winds, meteoritic impacts, and other processes can propel atoms into space, where they drift among stars and galaxies. These atoms, once part of living organisms, may become incorporated into cosmic dust, forming the building blocks for new celestial bodies. This migration reflects the enduring nature of atoms, capable of persisting across vast spans of time and space. The long-term stability of atoms ensures their participation in these extensive cycles. While most atoms remain stable, some undergo transformations, such as radioactive decay. Isotopes like carbon-14 decay into other elements over thousands of years, contributing to both scientific understanding and natural processes. Other atoms, like those in the iron core of the Earth or the oxygen in the atmosphere, persist unchanged for billions of years, maintaining their roles in planetary systems. The cosmic journey of atoms is an extraordinary tale, one that spans the vast expanses of time and space and underscores their fundamental role as the building blocks of the universe. Each atom, no matter how simple or complex, carries within it a rich history, a story that stretches back to the very beginning of the universe itself. At the birth of the universe, during the Big Bang, conditions were intense, with temperatures and energies so high that the universe was a hot, dense soup of elementary particles. As the universe cooled, the first atoms began to form, primarily hydrogen and helium, the lightest and simplest elements. These primordial atoms were the seeds of everything that would later come into existence: stars, galaxies, planets, and eventually, life. The formation of hydrogen and helium marked the beginning of cosmic history. These light elements, in combination with the forces of gravity, began to coalesce into the first stars. These stars, in their life cycle of birth, life, and death, played a critical role in shaping the future of the universe. Through a process known as stellar nucleosynthesis, these stars fused lighter elements like hydrogen and helium into heavier elements such as carbon, oxygen, and nitrogen, which are the building blocks of life. As stars underwent their evolution, some eventually reached the end of their lives and exploded in violent events called supernovae, scattering the newly created elements across space. This distribution of elements enriched the universe's chemical diversity, allowing for the formation of new stars, planets, and ultimately, complex molecules. These processes are responsible for the creation of all the elements heavier than helium, which form the very material fabric of the universe. These elements, once scattered across the cosmos, became incorporated into the next generation of stars and planetary systems, including our own solar system. On a microscopic level, atoms continue to be the fundamental units of matter, each with its own set of unique characteristics determined by its atomic structure, such as the number of protons, neutrons, and electrons that define it. These elements formed through the stellar processes laid the groundwork for the formation of planets, moons, and other celestial bodies. The atoms that make up Earth, for example, originated from ancient stars that existed long before our planet's formation. Some of the atoms that comprise our bodies, carbon, nitrogen, oxygen, came from the same stellar explosions that seeded the formation of the Earth itself. The cosmic journey of atoms took a new turn when these building blocks began to interact in increasingly complex ways. As stars and planets formed, atoms began to combine into molecules, leading to the emergence of the first organic compounds. On Earth, this process eventually led to the formation of the molecules of life, such as proteins, nucleic acids, and carbohydrates. These complex molecules, made from the same elements that were forged in the cores of stars, are the foundation of all living organisms. The atoms that once formed the first hydrogen and helium molecules now make up the very cells of every living organism, bridging the gap between the microscopic and macroscopic realms of existence. This connection between the microscopic and macroscopic realms highlights the profound significance of atoms in the biosphere. Atoms are not only the fundamental constituents of matter, but also the drivers of the biological processes that sustain life. In biological systems, atoms combine to form macromolecules such as DNA, which carries the instructions for life, and proteins, which perform the vast array of functions necessary for living organisms to thrive. These molecules are the products of countless atoms interacting in a precise and coordinated manner, forming the building blocks that give rise to the complexity of life. The same atoms that form the planets and stars are found in the molecules of life on Earth, linking the microcosm of subatomic particles with the macroscopic world of galaxies, stars, and living organisms. This universal connection underscores the interdependence of all matter, from the smallest quarks and atoms to the largest galaxies. The atoms that exist within us today were part of the early universe, forged in stars that lived and died long before the Earth came into being. These same atoms continue to shape the future of the universe as new stars are born and new planets are formed, continuing the cosmic cycle of creation, transformation, and rebirth. This journey of atoms also speaks to the unity of the universe, where the processes that govern the formation of the smallest particles are the same processes that shape the large-scale structure of the cosmos. The elements that make up life, such as carbon, hydrogen, oxygen, and nitrogen, are found throughout the universe, in distant stars, gas clouds, and even in the interstellar medium. The chemical diversity that exists in the universe is the result of millions of years of star formation, nucleosynthesis, and the recycling of matter through various cosmic events, ensuring that atoms continue to play an essential role in the unfolding story of the cosmos. Ultimately, the cosmic journey of atoms is a story of transformation. From the early moments of the Big Bang to the formation of stars and galaxies, to the emergence of life and the complex chemistry that sustains it. The atoms that formed in the early universe have traveled through time and space, interacting and combining in ways that have given rise to everything we know: stars, planets, and life itself. From the simplest hydrogen atom to the most complex organic molecule, the journey of atoms reflects the continuity of the universe and the ever-present interconnectedness of all matter, no matter the scale. As we continue to explore the cosmos, we find that the same processes that shape the formation of the universe also govern the creation of life, revealing a deep and fundamental connection between the microcosm and the macrocosm. Atoms also serve as silent witnesses to the universe's history. Their stability allows them to persist through eons, preserving records of cosmic events. For instance, isotopic ratios in rocks and ice cores reveal details about Earth's climate history, while the elemental composition of stars provides insights into galactic evolution. These atomic archives connect us to the cosmos, offering a glimpse into the processes that shaped our existence. The connection between atoms and the cosmic scale serves as a powerful reminder of the unity of nature's principles. At first glance, the vastness of the cosmos and the minuteness of atomic particles may seem worlds apart, yet they are fundamentally linked through the same governing forces and principles. The forces that dictate how atoms interact with one another, such as the strong nuclear force, electromagnetic force, and gravitational force, also operate on the grand scale of galaxies, stars, and planetary systems. This interconnectedness between the microscopic and macroscopic realms underscores the fundamental interdependence of all aspects of the natural world. At the atomic level, the forces responsible for the interactions between protons, neutrons, and electrons are essential for the existence and behavior of atoms. The strong nuclear force binds protons and neutrons together in the nucleus, while the electromagnetic force governs the interaction between positively charged protons and negatively charged electrons. Together, these forces maintain the structure of atoms and enable them to form the matter that makes up everything we see and touch. Without these forces, atoms would not exist in the stable forms that allow for the complexity of matter and chemistry we observe in the world around us. Interestingly, these same forces, albeit on vastly larger scales, influence the behavior of galaxies and stars. For instance, the gravitational force, which governs the motion of celestial bodies, can be thought of as a reflection of the attractive forces between particles at the atomic level. Just as electromagnetic forces drive the interaction of electrons within atoms, gravitational forces drive the formation and dynamics of entire galaxies. Stars, like atoms, undergo a process of fusion, where lighter elements like hydrogen and helium combine under immense pressure and temperature to form heavier elements, releasing energy that powers the stars. The process of stellar nucleosynthesis, where atomic nuclei combine to form new elements, is a cosmic-scale manifestation of atomic interactions. Moreover, the laws of physics that govern atomic behavior, such as quantum mechanics, have their counterparts on the cosmic scale. The principles of quantum theory, which describe how particles behave at microscopic scales with uncertainty and wave-particle duality, play a role in understanding phenomena like black holes, neutron stars, and cosmological expansion. These quantum effects can influence the structure of space-time and the fundamental forces that shape the universe. Quantum fluctuations, for instance, are believed to have played a role in the early universe, potentially contributing to the distribution of matter across the cosmos. The interplay between the forces of nature at the atomic and cosmic scales highlights the profound interdependence between the microscopic and macroscopic worlds. Just as the interaction of atomic particles shapes the formation of elements and molecules, the behavior of these elements and molecules on a larger scale influences the formation of stars and planets, and ultimately, life itself. The materials forged in the hearts of stars are the very building blocks of planets, moons, and living organisms. Atoms and molecules are the foundation of the material universe, but the stars that produce them are the driving forces that give rise to the larger structure of the universe. For example, the nucleosynthesis of elements in stars and supernovae enriches the interstellar medium with heavier elements, which are then incorporated into the formation of new stellar systems and planetary bodies. The carbon, oxygen, and nitrogen atoms that form the molecules of life on Earth were produced in the hearts of ancient stars and scattered across space by supernovae. Over billions of years, these elements have come together to form the complex chemistry that sustains life, making the evolution of life intrinsically tied to cosmic events on an atomic scale. The expansion of the universe, driven by dark energy, is another example of how forces that influence the atomic scale can have far-reaching consequences on the cosmic scale. Dark energy, which is responsible for the accelerated expansion of the universe, may be a manifestation of fundamental principles that also govern the behavior of particles at the quantum level. The interplay between these forces has resulted in a dynamic universe where galaxies and stars form, evolve, and eventually die, while atoms persist and undergo transformation through processes like fusion and fission. The expansion of space itself is shaped by the same fundamental forces that govern the behavior of particles, illustrating how atomic interactions reverberate throughout the cosmos. Furthermore, the evolution of the universe is a continuous process of matter being broken down and reformed, much like the cycle of atoms that form and reform through various processes in the universe. Just as atoms can be broken apart through chemical reactions and nuclear fission, the cosmic cycle involves the creation and destruction of stars, the birth of new elements, and the redistribution of matter across space. This dynamic relationship between creation and destruction mirrors the atomic world's constant interaction between bonding and breaking, where atoms come together to form more complex structures, only to be torn apart and reassembled in new forms. The formation of the solar system itself offers another striking example of this connection. The dust and gas from older stars, containing atoms that had undergone countless cycles of fusion and supernova explosions, coalesced under the influence of gravity to form the planets and other bodies in our solar system. The materials that make up Earth and its biosphere originated from these same atomic processes, illustrating the cyclical nature of creation in both the atomic and cosmic realms. This connection also extends to human beings. The atoms that make up our bodies were once part of ancient stars, and their journey through the universe reflects the interconnectedness of all matter. The carbon-based life forms that exist on Earth are composed of elements that were produced in stellar nucleosynthesis and spread across the universe over eons. In this way, the atoms within us are not separate from the universe. They are part of its larger cosmic story. The idea that the forces governing atomic interactions shape the universe's large-scale structure is a profound reminder of the unity of nature. From the behavior of subatomic particles to the dynamics of galaxies, the same physical principles apply across all scales. This unity reflects the elegance and simplicity of the natural world, where the same forces that govern the formation of matter on the smallest scales also shape the structure and evolution of the cosmos itself. Whether on the scale of atomic nuclei or galaxies, the principles that govern the behavior of matter ensure the cohesion of the universe, where the microcosm and macrocosm are inseparable, bound together by the forces of nature. Ultimately, the profound interdependence of the microscopic and macroscopic worlds is a testimony to the cohesive nature of the universe. Atoms, governed by the fundamental forces of physics, form the basic building blocks of matter, and these very atoms shape the grand structure of the cosmos. The interactions at the atomic level directly influence the formation of galaxies, stars, and planets, and the processes on a cosmic scale echo the forces that govern the subatomic realm. In this sense, the universe is a unified whole, where the behavior of individual particles on the smallest scales has profound effects on the large-scale evolution of the cosmos, and vice versa. As we contemplate the journey and transformation of atoms, we are reminded of their role as the fundamental units of existence. From forming the molecules of life to drifting among the stars, atoms embody the continuity and dynamism of the cosmos. Their enduring presence bridges the past, present, and future, weaving a narrative of connection and transformation that defines the very essence of reality. We'd love to hear your thoughts in the comments below. If you found this explanation fascinating, make sure to like, share, and subscribe for more captivating content. Thank you for journeying with us here on Frontiers of Infinity.